The second moment, basics. After the expectations, the most vital statistic for a random variable x is the variance. We denote it VAR of x. It is denoted by VAR of x equals to the expectations of x minus the expectations of x, then to the square, and measures how spread out x is from its expectation. We should generally, following standard practice, let mu denote expectation and sigma square denote variance. The positive square root sigma of the variance is called the standard deviation. With this notation, here is our basic tool. Theorem 4.1.1, Chebyshev's inequality. For any positive lambda, the probability that the difference between x and mu, which is greater than or equals to lambda times sigma, is less than or equals to 1 over lambda square. And here's a simple proof. Proof that by definition, the sigma square is equals to the variance of x. And we can just expand by the definition of variance of x, which is the expectations of the results of x minus mu then to the square for all possible x. So if we draw the picture instead of a mic, you can see that if you assume that the y coordinate is just fit into the lines of when the values is equals to mu, then it's a symmetric and it's like a U shape of curve. So if you talk about, if you just view the probability of x minus mu, whose absolute value which is greater than or equals to lambda sigma, then you will see that maybe the middle part of this U shape is blocked. But then after some part which is far from lambda sigma to the mu, we time with the values lambda square, sigma square, which means that the growing speed of the right hand side of this formula is far less than the left hand side, that is the expectations of x minus mu to the square. So that's why there is a greater than or equals to. So here's the proof. Okay, the use of Chebyshev's inequality is called the second moment method. Chebyshev's inequality is best possible when no additional restrictions are placed on x, as x may be mu plus lambda times sigma and mu minus lambda times sigma, with a probability 1 over 2 lambda square and otherwise mu. Note, however, that when x is a normal distribution with the mean mu and the standard deviation sigma, then the probability of, that is the term that we just saw before, the probability of the absolute values between x and mu, which is greater than or equals to lambda sigma, is equals to 2 times the integrations of the following function, 1 over the square root of 2 pi times e to the exponent of minus t squared divided by 2. And the integration is starting from lambda to infinity. Note that such a normal distribution is sometimes we call it a standard normal CDF, because we assume that the random variable with the variance 1 and the mean 0. Okay. Now, and for lambda large, this quantity is asymptotically the square root of 2 divided by pi times e to the exponent minus lambda squared divided by 2, then divided by lambda, because we have do the integrations of the calculus, which is significantly smaller than 1 over lambda squared. In chapters 7 and 8, we shall see examples where x is the sum of nearly independent random variables, and these better bounds can apply. So suppose we have a decomposition, x equals to x1 plus x2 and so on, plus xm. Then the variance of x may be computed by the formula. VR of x is equals to the summations of a VAR of xi for each all possible xi of the decomposition, where the summation is summing with index I starting from 1 to n for all of them, plus the covariance, the summations of covariance between xi and xj when I is not equals to j. This is in the fourth lines of our keynote. Here, the second sum is over ordered pairs, and the covariance cov of yz is defined by cov of yz is equals to expectations of y times z minus the expectations of y times the expectations of z. In general, if y, z are independent, then covariance of yz is equals to 0 because they are independent. This often simplifies variance calculations considerably. Now suppose further, as will generally be the case in our application, that the xi are indicator random variables, i.e. that xi is equals to 1 if a certain event ai holds, and otherwise xi is equals to 0. You see, when we explain the normal distribution assumption, we've already talked about this before. If xi is 1 with the probability pi, which is defined as pr of ai, then the variance of xi is equals to pi times 1 minus pi, which is definitely less than equals to pi, because pi is some variable which is less than equals to 1, and which is equals to expectations of xi. So which means that the variance of xi is less than or equals to the expectations of xi. And so the variance of x is less than equals to the expectations of x plus the covariance, the summations of covariance of xi and xj, where the summation is summing for all pairs of I which and all pairs of ij which are different to each other. So here is the basic truth Chebyshev's inequality that we learned from the second moment method. And later on we will introduce you an applications of second moment method.